Okay.
Okay.
Good afternoon, everybody. Many thanks for joining us for today's Tech Talk as part of our Knowledge Learning programme. Today's Tech Talk is on hybrid strengthening. I'm Steve Musa, one of the project team. I'm joined by our Technical Director, Jay.
Good afternoon, everyone.
So let's jump straight into it then, Jay. Hybrid strengthening. Why would we look to use carbon fibre just generally anyway?
Yeah, carbon fiber strengthening is becoming quite popular nowadays for strengthening of different structural elements, purely because it's a very high strength and lightweight material. So just to give you a feel in terms of number, it is at least 3 to 4 times stronger than steel, and it is 7 to 8 times lighter than steel. It can be used for strengthening concrete structures, steel, wrought iron, cast iron, even on timber structures. So you can use pretty much all type of structural construction material using FRP. And that is the reason that it is becoming quite popular these days.
We are seeing a lot of main contractors going to designers, asking the designer to, can they have a carbon fibre solution? That's not just for the design front, but the economics as well.
Yeah, it is. It is a very economical solution if we see the whole cost in terms of material, labor, disruption to the structure, and most importantly, time in doing that strengthening. So the reason why main contractors are approaching designers and architects to look into CFRP strengthening of various elements is purely because of time. So their program time can be significantly reduced by doing strengthening using FRP. Also, it doesn't need a lot of temporary works, lifting of steel section in place and everything, and that's the reason they approach them. And it is ultimately, if they see the whole cost, it is the most economical solution available in the industry at the moment.
So we're going to talk about the hybrid strengthening system. So we need to look a bit more about the approvals and guidelines and the design of carbon fibre.
Yeah, so this is mainly to talk about the approvals and acceptance of carbon fiber strengthening system, along with the design guidelines for carbon fiber strengthening. So generally, if you're proposing to use carbon fiber strengthening on any of the projects here in the UK, the minimum approval those systems needs to have is a CE marking. So that's the least approval they need to have.
Okay.
In addition to that, there are some specific approval, construction specific approvals available, which some of the systems have got. For example, ICC ESR listing, which is the International Code of Council, the governing body for design codes around the world. They provide an approval, and some of the systems have got that. UL approval is basically for fire protection. So if somebody comes to your project or something and say that I have a fire protection system for fire protecting CFRP strengthening system or FRP in general, they should look out for this UL rating, because that UL is the authority which provides that approval.
It's quite an interesting point, that, because a lot of engineers, a lot of companies are under the impression that you can't fire protect carbon fibre, and that's not right, is it?
Yeah, that was a misconception until some research has been done using fire protection systems onto the FRP, and some special fire protection systems were developed which can work on those sort of temperature and everything. So there are systems available which can be used for fire protecting FRP if required, and as I said, they are rated and tested by UL. In terms of design, if you're designing it in the UK, then the document to follow is this Concrete Society document TR55. That's the design guideline to design FRP in the UK. TR57 gives you application guidelines. So these are the two guidelines for the UK. Then we have ACI 440, which is American Concrete Institute document, majorly followed in America, but everybody follows ACI. And FIB 1814, which is followed in the rest of the Europe. So these are the three main design guidelines which are used worldwide to design FRP. But currently we have just design guidelines. We don't have a design code. That's why we don't see pretty much all the structural engineers designing CFRP strengthening system, because there is not a set code available.
I believe there's a lot of work going on in the background, and we're expecting a code in the near future.
Yeah, soon. So the team which recently finished the TR55 edition and the recent upgrade in the ACI 440 committee as well, they both are looking into producing a design code, which will hopefully be out later on this year. So we should soon have a Eurocode 2 with an annexure for FRP design, and an American Concrete Institute design code as well for FRP design.
So we're gonna now look at the general sort of design principles, basic design principles. You give a bit more detail on that?
Yeah. So on the slide we can see the stress strain behavior of FRP and compared with the mild steel. Usually steel is designed on the yield stress, and the top green line shows the behavior of carbon fiber, bottom green line shows behavior of glass fiber. From this curve we could see that carbon is stronger than steel, so when I said it is 3 to 4 times stronger, you can see it's evident on this stress strain distribution. The glass fiber has better deformability or ductility, if you like. So depending on this curve and the requirement, it is decided which material to use and at what strain level it should be designed. So FRP is a strain limit design. We don't design FRP on the tensile stresses given on the data sheet. So that's the one thing to note. So in a very simple way, if we try and understand FRP design, then we only use the modulus of material and the thickness of material from the data sheet.
Okay.
Then the strain is derived by the designer depending on the guideline they are following. That design strain is multiplied with the modulus that will give us a design stress. So we may end up deriving design stress for each and every element on every project. So for that reason, FRP is a strain limit design. The other reason is that, as we can see, that FRP in carbon fiber and steel, or any FRP for that matter, has a linear elastic behavior, or it's a straight line until it reaches the end. In other words, there is no warning before FRP fails, or there is no yield point. So ultimate failure is brittle in nature, and to avoid that failure, FRP design is a strain limit design.
Okay, so that's a key point that designers should be aware of. So then we're looking at sort of dry versus cured when we're looking at the design properties, yeah?
Yeah, so FRP system, or especially carbon fiber reinforced polymers or glass fiber reinforced polymers, are basically composite materials. So there are two materials mixed together to make FRP. So we have a dry fiber that is mixed with epoxy matrix. When it cures, it becomes a laminate, and that laminate is called FRP. So in the design, we should always consider this final cured laminate property and not dry fiber, because they are significantly higher and not the true expression of what we are going to get on our project once it is mixed with epoxy. So it should always be designed on these final cured laminate property and not dry fiber.
Okay. So we actually look at some case studies now, some projects where we've actually used a hybrid strengthening system.
Yeah, so hybrid strengthening system where carbon fiber is used alongside with traditional materials such as steel and concrete. So those are the situations where, these are some of the projects where we use both together. The reason for that is that FRP, even though it's a very strong material and everything, and it's a very good material, but it has its own limitation as well. So to get over those limitations and everything, sometimes you have to combine different types of strengthening techniques, and that's where both steel and FRP are used together.
So this project is the Clayton Hotel in Birmingham. Sort of what was the issues here?
Yeah, so it's an existing hotel, and they were adding another story on one of the wings of the hotel. So it was going to remain fully operational while the work carries on and everything. So because of the addition of the new story, the beams needed strengthening, the columns needed strengthening for additional loads, but also the slabs needed strengthening for punching shear. And the solution proposed by project engineer was, as we can see on the sketch on the right hand side, it was post drill fixed shear studs. Now, because it was a pre-stressed slab, and in a pre-stressed slab, drilling is not good, because you may damage the tendons and everything. And as soon as you drill, you release some stresses. So you can damage structure a lot more by doing this kind of technique. And also, if you want to avoid the damaging of the tendons and everything, you cannot define a certain center of these shear studs and everything. So this was the solution which could not be practically done on site. So the project engineer with whom we were already working for beam strengthening and column strengthening, they approached us to check whether carbon fiber strengthening will be feasible here. So we said it can be feasible, but in some situation the punching shear failure was at the column perimeter. And in that instance, they had to design these steel collars, as we can see on the bottom image on the left hand side, to move that punching shear perimeter away. Then the carbon fiber was applied on top to provide additional tensile reinforcement on top of the slab. So that's how both material were used for just one type of strengthening there.
The second example was shown. It was quite a large project. I think it's the second biggest project we've worked on in the UK. It's Blythe Road. Again, combination of using steel and carbon fibre. Yeah.
It is, yeah. So again, it's an example of a new build structure needing strengthening. So the issue there was that after the construction of these concrete frames, there are 3 concrete frames, as we could see on the leftmost image, one front, one at the back, and one on the left hand side of that. So those 3 frames were constructed in 2014. After the construction of these frames, contractor was working there, has gone into administration. So before passing his work to the new contractor, there was some investigation work done, and they found that there is some reinforcement is missing in the flat slabs, and there was around 385 plus areas where the reinforcement was not adequate as it should have been according to the design. So we worked with new consulting engineer, designed each and every area individually to provide those additional reinforcement, because the other solution was to demolish and rebuild, which we can see from economics point of view as well. It is a much more expensive solution. At the same time, from sustainability point of view as well, we'll end up generating a lot more CO2 emission if we demolish and rebuild this. So we had to work with the new consulting engineer, design each and every area individually for the equivalent amount of reinforcement. It was a quite involved design, and we worked in partnership with the project engineer. So they provided us the output in terms of in what area what's missing, to what extent, and everything, and then we calculated the required amount of CFRP in those areas and developed our design drawings and everything. So that's how the strengthening was done there. But there were some areas where the required reinforcement was very high, and the carbon fiber was not just visible, and also some areas where the slab was failing significantly in punching shear. So in those areas, they had to use traditional steel sections as well as post-roll fixed shear studs for punching shear strengthening. So that's why this strengthening was also more or less hybrid strengthening, where both steel and carbon fiber was used. But in 90% of the project, CFRP strengthening system was used, and the remaining 10% was dealt with the carbon fiber, with the steel and post-roll fixed shear studs.
Yeah. Okay, this is quite an interesting project that we had a couple of years ago in London.
Yeah, so this is another project where an existing building, because of the new stories they were adding onto the structure and everything, and additional loads onto the column needed strengthening for axial load, which was done using carbon fiber. So we strengthened this column in the hoop direction using FRP. But as well as, when they were assessing the structure, investigation was done, they also found that the punching shear reinforcement in the slab was not adequate as per the current codes and the design requirements. So they had to do punching shear strengthening. So again, both type of strengthening techniques were used. Traditional method using these shear studs, which was also done by us. So it was designed by project engineer but installed by us. And then we designed the CFRP strengthening for the columns. So as you could see, the column were first wrapped with carbon fiber strengthening system, and then they were painted over to get the similar sort of finish as in the surrounding areas. So again, both techniques were used there: punching shear strengthening with the post-roll fixed shear studs, and column strengthening with the carbon fiber.
One of the key areas for the application and use of carbon fibre is the process of application, and we're going to look at now the 5 stages on a brief time-lapse video.
Yeah, so the application is key in any FRP strengthening project. If you can design it as well as you want, but if it is not installed correctly, it will not work as it is designed for. For that reason, we do not subcontract the application. It is done by our own guys who are employed by us, purely just to have that control on the application as well. But the process is, first you prepare the surface, which is normally done by diamond grinding, followed on by cleaning of the area, because you need a dust-free surface to apply carbon fiber. Then they do the priming of the concrete, which is done using pure epoxy, so it can soak into concrete. Then they apply the first coat of thickened epoxy, which is the white color epoxy we are seeing, and they unroll the first layer of carbon fiber. Then another coat of epoxy, then another layer, and that's how they build up the number of layers according to the design. Now, usually if you're applying FRP on a vertical or an overhead application, then in that case you're limited in applying 3 layers of carbon fiber in one day in one shift. After that, you have to wait for it to initially set, which will be 4 to 6 hours, and then you can come back and apply further layers. It usually cures in ambient condition in 72 hours. so you can reload your structure back to its new capacity in 3 days time. The other thing to note here is that the carbon fiber these guys are installing is saturated in a different area on same site. So when they are applying it, it's in wet condition. That's why this application is called wet layup method. Now there are still people out there who do dry layup. So in dry layup, they just prime the area with the pure epoxy and try and patch a dry fiber on that primed area using their hands, and then put another coat of epoxy on that dry fiber. Now that by doing that, they cannot guarantee the 100% resin impregnation through every fiber, and that dryness will lead to a debonding or delamination failure. So to avoid that, application has to be a wet layup method, especially in a fabric system. So that's one of the key point people should make note of, that on any of their project, if contractor is doing FRP application, that needs to be wet layup method.
And you see the general layout of the carbon fibre, that's actually specified on the drawing when you're looking at sort of the various lengths and the positions.
Yeah, exactly. So that when we prepare our drawings, we show this on our drawing, that how it will be laid, in which direction, how many layers, to what length, and all those things, and everything will be shown onto the drawings.
And then the final finish for when they finish the carbon fibre itself, it can be screeded over and painted whenever there's no issues.
Once the carbon fiber is installed and it is cured, you can plaster it, paint it, render it, you can do anything on top of it. In this particular instance, they screeded back over it, so it was covered under the screed. So yeah, you can do whatever you want.
Okay, that's great. So that's our tech talk today on using hybrid systems. If there's any information, additional information you would like, please go to our website. There's a lot of information there, our videos or our YouTube channel. But thank you very much for joining us today. If you'd like a certificate, please scan the QR code and it will ping to us and we'll get that off to you. So thanks very much for joining us today. Thank you.
Thank you.